Tassi. Last time I was here, I was a student, so now the tables have turned. I encourage all of you to get the most out of it. For me, at least, it was a great experience. Indeed, many of my closest friends now as postdocs and faculty members I met at Tassi in 2010, going on hikes and going to the 2 a.m. pizza place and so on. So, live it up. All right. The basic goal of these lectures is to understand AdS CFT as a quantum theory of gravity. Many applications of AdS CFT, some of which Joanna referred to, are based on using classical gravity in the bulk to study properties of the boundary theory. That's not what I'm interested in. I want to be doing bulk quantum mechanics. So, in particular, I want to focus on a few basic questions. So how does bulk effective field theory emerge in CFT language? Which CFTs does it emerge from? And what are the limitations on this emergence? Okay, and I'll admit from the beginning that I don't have completely satisfactory answers to any of these questions. On some level, that's good because it means it's a good thing to lecture about, because maybe some of you guys will come up with better answers for these questions, now or in the future. But hopefully, I will convince you that I at least know something about it. All right. For the most part, I'm going to be describing the correspondence at fixed time in Lorentzian signature. The main technical results, which I'll try to get to by the end of the lecture series, and since there are 5 lectures, I'm optimistic that I'll get to at least some of them, is the recent interpretation of AdS CFT in terms of quantum error-correcting codes, and its illustration using exactly soluble models of holography. So within that language, these kinds of questions become very accessible. Hopefully I'll convince you of that as we go along. So don't worry if you don't know what words like quantum error correcting code mean. You will hopefully by the end of the week. And then, time permitting, I'll also try to discuss the quantum version of the Ryu-Takayanagi formula, which is something I guess most of you have heard about. So the Ryu-Takayanagi formula, at least, and I'll try to convince you that the quantum generalization of the Ryu-Takayanagi formula is closely related to these questions and also closely related to quantum error correction. Since AdS CFT is so important, though, I thought that even though Joanna is already doing some of the same things, I thought I would start from the beginning and give you my version of AdS CFT. What the statements are, what it means to check it, and so on. My presentation may be somewhat non-standard, so hopefully even the people here who are experts will still get something out of it. So the basic idea is that quantum gravity in asymptotically AdS space is isomorphic to a conformal field theory in d-dimensional space-time. So I'll state, and this is here. This is AdS d+1. So I'll start by studying the two sides of this separately, and then we'll discuss how to fit them together. So let me start with AdS. And by the way, I like questions, so you know, questions are good. I mean, if questions mean that we don't say everything that I was planning to say, that's fine. It's still better because probably we learn more when there's active participation. So don't hold back. Okay, so AdS. So let's just start. So probably this everyone knows, but let me still just say it. So AdS is the maximally symmetric spacetime of constant negative curvature. You can obtain it as a submanifold. So AdS d plus 1 you can obtain as a submanifold of d plus 2-dimensional Minkowski space in 2, d signature. So indeed, if you start with the metric minus dt1 squared minus dt2 squared, so 2 time coordinates, dx1 squared, dxd squared. Okay, so that's the metric of d plus 2-dimensional Minkowski space in 2, d signature. Then if you define a surface t1 squared plus t2 squared minus xd squared is equal to L squared. So that's something like, you know, if here's T1 and here's T2 and here's one of the x directions, then this is some sort of hyperboloid of revolution, something like that. Then this submanifold, or more carefully, its covering space, define AdS d plus 1. So let me just say that a little more explicitly. So if I choose coordinates, T1, r squared plus 1, cosine of t, T2 is L plus 1 sine of t, and I take the square of x to be r squared. So you can check that if I substitute this into this equation, it's a true equation. So then these coordinates, t and r, and then, did I knock the thing down? This is going to be a recurring problem, I'm sure. All right. Well, if it keeps falling, I'll just stop using it. Actually, is that bad for the video recording? Okay, yeah, because I'm loud, but I don't, you know, I know them not that loud. Okay. All right. Okay, so if we define these coordinates, and then we compute the induced metric onto this submanifold from this coordinate transformations, we just get the usual AdS metric in so-called global coordinates. What? Here? Oh, yes, you're right. Very good. Indeed. Okay, and so this probably everyone has seen. This is a metric of AdS in global coordinates. And now the comment I made about the covering space is that T as defined here is a periodic coordinate, but we just choose it to instead be to have a range from minus infinity to infinity, and that's the thing that we actually call anti-de Sitter space. Otherwise, there would be closed time-like curves, and those are for science fiction authors, not physicists. All right. So let's just comment on a few basic properties of this geometry. So the first comment is that this is a solution of Einstein's equation with negative vacuum energy. Rho naught is minus d times d minus 1 over 16 pi g L squared. Yeah?
Are you going to allow field configurations that don't have the same value plus
No, well, yeah, well, now so the boundary conditions are now at minus infinity and plus infinity. And so then whatever happens at minus infinity is related to what happens at plus infinity by solving the equations of motion. So it's not really a boundary condition, it's dynamics that relates the two. But indeed, but in particular, like if I have a field or something, I won't demand that at t equals 0, I get the same thing that I would. The value of the field is not the same as it would have been at 2 pi, right? Whereas had we not taken the covering space, that would have been required. And indeed, in most of the examples of AdS CFT, there are definitely operators that don't obey that periodicity going from 0 to 2 pi. So it's important that we take the covering. Okay. Right. Okay. So good. So from now on, for the most part, I'm going to set this AdS radius to 1 and just work in units where L equals 1. But we'll just keep in mind that its relationship to the vacuum energy involves this g Newton here, so it involves the Planck scale. Okay, so that's comment number 1. Comment number 2 is that this has an isometry group. So it's pretty easy to guess what the isometry group is because we started with this d plus 2-dimensional Minkowski space. So it's just going to be SOD, 2. It's the Lorentz group, but with 2 time-like directions instead of 1. The third comment is that well, we can simplify we can clarify the causal structure of this geometry by defining a new coordinate r equals tangent of rho. So then rho is going to go between 0 and pi over 2. And if we do this change of coordinates, what you find is that ds squared is 1 over cosine squared rho times minus dt squared plus d rho squared plus sine squared rho d omega d minus 1 squared. So the nice thing about this is that you see it's minus dt squared plus d rho squared. So null geodesics in the radial direction, just move it 45-degree lines in terms of this t and rho coordinates. Okay. And if you don't know, you should prove to yourself in the privacy of your dorm room in Kittredge that null geodesics don't care about an overall scalar function multiplying the metric. So this metric has the same null geodesics as this one. So that means that we can draw a picture. So here I'll draw it for AdS3 just because I'm graphically challenged. So here time is going up this way from minus infinity to infinity, and so this spacetime is like a solid cylinder. So we have the r coordinate is this radial coordinate here, and then there are these angular coordinates going around this way. And then what this tells us is that if we're sitting in the center of the space here, and we shine out a laser pointer, it goes out to the boundary, and then it comes back to us at finite time. And in fact, at time delta t is pi, right? Because it was pi over 2 to get to the edge here, and then another pi over 2 to get back. So you can think of living in AdS as like living inside the can of soup. And it's a little deceptive because if you compute the spatial volume at fixed time, it's infinite, but nonetheless signals can get out to the boundary and come back to you in finite time. So it's sort of a box, but not a box. But actually, it's kind of better to think of it as a box, as we'll see in more detail soon. So then finally, continuing. What this rho coordinate makes very clear is that there's really this asymptotic boundary at rho equals pi over 2. So rho equals pi over 2, we can define it as the conformal asymptotic boundary. And it has topology r times SD minus 2. And actually, it doesn't just have that topology. We can think of it as having the round metric on SD minus 2 just times the times a flat line. So it really is just the boundary of the cylinder. What? Oh, yeah, well, I guess they're, yeah, I can write rho if you like. They're monotonically related. Yeah. Okay. So that's probably, that there's only so much one can say about AdS, so probably we said enough about it. Now, it's important that when I stated the correspondence, though, I didn't say AdS d plus 1. I said A AdS d plus 1. So the extra A stands for asymptotically AdS. And the asymptotically is very important, because without the asymptotically, this is a very boring theory of gravity, right? It's just that, hey, look, it's AdS, okay, we're done, right? I mean, you can't put anything in there. If you did, it would change the geometry. Okay, so to have an interesting geometry, we need to relax. This geometry is too strict. We need to relax it, right? So asymptotically AdS geometries are defined as geometries which have a conformal boundary, which has this metric, and which inside the metric approaches this one as we approach the boundary. But it can be doing something else inside. Okay. Now, we could give a whole lecture about precisely what it means to say approaches. How fast does it approach it, right? Which components of the metric have to approach it in what way? And there's a whole industry about that. I think I won't give that lecture, but it's a very interesting exercise to go through. There's a paper which by Hainaut and Titelboim, which in the lecture notes, which should hopefully appear on the website soon, you'll see the reference, which explains that in great detail. And anyone who cares about AdS CFT should know that paper backwards and forwards. But unfortunately, I don't have time to discuss it. But they define carefully what it means to be asymptotically AdS. Okay. So I will, though, let me give an example of something which is only asymptotically AdS. So this will be so this will be the AdS Schwarzschild geometry. So now we have some function f of r, dt squared, plus dr squared over the same function f of r, plus r squared d omega d minus 1. And now this f of r is 1 plus r squared minus 16 pi gm over d minus 1 omega d minus 1 times 1 over r to the d minus 2. Okay. Now, this coefficient here is chosen so that this m that I wrote here is the asymptotic energy of this solution, right? So if you want to think of this as being like a black hole or a star or something, then this is the mass of that star with respect to the time defined at infinity. So another fun exercise. Find this coefficient and convince yourself that I got it right. In order to do that, it's harder than you think. In order to do that, you have to read that other paper and convince yourself that you know how to define energy in asymptotically AdS spacetime. But when you're done, you'll find that I got the right coefficient, hopefully. Now, in fact, this solution, well, it's asymptotically AdS, but if you stare at it for too long, you'll convince yourself that it actually has two asymptotic AdS boundaries. So the full geometry of this solution is this wormhole geometry, where you have an AdS boundary here, another AdS boundary here, and they're connected through the middle. So this geometry actually, we'll see, doesn't describe a state of just one copy of the CFT on this sphere, although I haven't said what the CFT is yet. But we can make something that's a little bit more kosher, which only has one AdS geometry, by, for example, having a star sitting in the center of AdS. And then this geometry is the right geometry outside of the star, and then it sort of smoothly closes off back into something like the center of Minkowski space inside of the star. And that'll be an honest-to-God asymptotically AdS geometry. Okay, and in case it wasn't obvious, right, you can see that when r is large, well, at least as long as d is greater than 2, which is necessary for this geometry to make sense, then it does approach this one at large r, okay, as promised. And it approaches it sufficiently fast in the sense of the paper that I said you should read. Okay, so very good. Let's see, how does this? Here we go. So now I want to explain one more thing about AdS before I turn to CFT. So the last thing I'm going to explain, maybe it's a little more involved, but it's one of those things where it's so important that I think we need to go through it. Okay, what we want to do now is to define the left-hand side of the duality is we want to do quantum gravity in asymptotically AdS spacetime. But that's kind of ambitious, so I'm going to start by just doing a free scalar field in AdS. And already we'll see that there's some fun things that happen. And clearly, if we can't do that anyways, we're not going to be able to do that. So let's start simple. Okay, so free scalar in AdS. Okay, so this theory, the Lagrangian is d mu phi, d nu phi, g mu nu, plus m squared phi squared, where the minus sign here means I'm using the correct metric sign convention. Various particle physicists sometimes use an incorrect metric sign convention. So then the equation of motion that follows from this is that if we take the curved space Laplacian acting on phi, which we can represent like this, acting on phi is equal to m squared phi. So the first thing we should do is get a sense of what the classical solutions of this equation look like. Those will eventually correspond to the particle-like excitations of the quantum field in AdS. But let's just first think about it classically. So to solve this equation classically, well, based on our experience with flat space, it seems the obvious thing that we should do, and turns out the correct thing to do, is to try to expand it in a set of modes where the different coordinates in that metric are decoupled. So we look for a family of solutions, the following form. So there is a radial function which depends only on r. We just decompose into frequencies in time, right? So you see this metric has a continuous shift symmetry of time. So expanding in these kinds of things is a good thing to do. And it's also rotationally invariant, so then we should expand also in spherical harmonics. These spherical harmonics are guys which obey del squared y, Lm is minus L times L plus D, I think minus 2 times y Lm. Okay. And that's the only thing you need to know about them. If you're bored, again, in your dorm, you can have fun constructing them in d dimensions, but I'll leave that for you. Okay. So then the idea is, okay, so we take this, right? So L and M are sort of the angular momentum quantum numbers. Omega is the frequency. Psi by symmetry turns out to depend only on omega and L. And then I mean, here we already know what these guys are. So the meat of this is going to be to find this psi of r. So we can figure that out by substituting this back into this equation of motion. For fun, maybe I'll write out the equation that you get for psi. So sorry, this will take a sec. So 1 plus r squared psi prime prime plus d minus 1 over r times 1 plus r squared plus 2r times psi prime plus omega squared over 1 plus r squared minus L times L plus D minus 2 over R squared minus M squared times psi is 0. Okay, another homework problem, derive it, but it's not too bad. You just have to use this property of the spherical harmonics. Okay, so now we're going to spend 5 minutes enjoying this equation. So anytime you see an equation like this and it looks complicated and you don't know what to do, Well, if you know about hypergeometric functions, you know what to do. But first, that should never be the first thing you do, even if you can do hypergeometric functions. The first thing you should do is you should look at the asymptotic solutions of this when r is large and r is small, because clearly then this equation is going to simplify. So indeed, when r is large, then this just becomes r squared psi prime prime plus d plus 1r psi prime minus m squared psi is 0. Okay, and this one maybe we can even solve in our heads. The solution is a power. So this has solutions which go like r to the minus d over 2 plus or minus a half square root of d squared plus 4m squared. And then when r is small, so then we have a different kind of equation. Instead, what we get is psi prime prime plus d minus 1 over r psi prime minus l plus d minus 2 over r squared psi is 0. And woohoo, this again has a power solution, which is that psi should go like r to the minus d minus 2 over 2 plus or minus square root of d minus 2 squared plus 4l, l plus d minus 2. Okay.
So over here you expanded phi in this basis.
Yeah, that's right. Yeah, then I just substituted this back in here, and for g mu nu, I use this metric. Yeah. And then, unless I made an algebra mistake, which is unlikely since I got the right answer, so I would have had to make 2 that canceled, this is the equation that you get. What? Yeah, there's a 1/2. Very good. Yes. Indeed. So now, to say more, now we have to think about these signs here. Sort of what do we expect for the signs? Okay. So at small r, it's pretty easy to figure out what the right sign is, because if we don't choose the plus sign, then this is actually divergent. R goes to 0, and so the solution is singular. So sign non-singular tells us that we need to have plus near r equals 0. Okay. The boundary conditions at infinity are more interesting, these ones. So there are these 2 options for how things can fall off with r. So roughly speaking, if you choose the plus sign, then it falls off faster with r. And if you choose the minus sign, then it falls off slower with r. So it turns out that if m squared is greater than 0, or equal to 0, and you want to have the theory be unitary, meaning that you don't want to have particles leaking out at infinity, then you also have to choose plus for the large r behavior. So if we take m squared greater than or equal to 0, and d greater than or equal to 2, then unitarity tells us that we need to take plus near r equals infinity. And so that's called the standard quantization, or the standard boundary conditions for the scalar in AdS. You can think of those as reflecting boundary conditions, right? So like if you're doing E and M, and you know, or even just a classical scalar field, and you impose Dirichlet boundary conditions on a surface, then it tells you that whatever waves come in have to be reflected back. And that's kind of what you want, because we want to have a closed theory of quantum gravity that makes sense and is unitary by itself in AdS. So we don't want things to be able to leak out at the boundary. If m squared is less than 0, then sometimes the minus sign is allowed, and that's called the alternate quantization. But since Igor is not here yet, I won't talk about it. He's one of the inventors of the alternate quantization. Well, really Dan Friedman, but okay, it was rediscovered by Igor and Edwin. Yeah?
Wait, so for m squared greater than 0, you can't do alternate quantization. Is that what
Yeah, that's right. Yeah, and from the boundary point of view, just since you sound like an expert, you'll see that the conformal dimension that you get if you pick the minus sign violates the unitarity bound. So the bulk statement, which I'll say a bit more in a sec, is that these solutions have to be Klein-Gordon normalizable. And that's the technical version of saying that stuff shouldn't be able to get out in infinity. And then the boundary version is that the operator has to obey the unitarity bound in the CFT. Okay, good. Now, since you all look like smart and experienced people, you probably know, for example, from your quantum mechanics class, that if you have a second order ODE and you impose a boundary condition both at one end and at the other end, then usually there's not a solution. So to have a solution, you need to tune one of the parameters in the system so that just by chance both of these are true at the same time. Okay, and the only continuous parameter we have to tune is this frequency here, right? The frequency that controls the time dependence of the solution. So in fact, if we want to satisfy both of these things, and now to derive this, you actually then have to go and learn about the hypergeometric functions, because you have to be able to match the asymptotic solution at one end to the asymptotic solution at the other. But so when you go back to Kittredge and you do that calculation, what you'll find is that this implies a quantization on the frequency. So omega has to be equal to omega NL, which is equal to delta, I'll say what delta is in a sec, plus L plus 2n. So here n is equal to 0, 1, 2, etc. And then delta is the power that appears here with the plus sign. So delta is d over 2 plus 1/2 square root of d squared plus 4m squared. Okay. So this is further evidence that you should think of the AdS as being like physics in a box. The frequencies are quantized of solutions of the wave equation inside. Right? So that's like what you learn if you solve a wave equation in a finite box. No, but I gave a physics reason for imposing the boundary conditions, though. I wanted it to be unitary.
Oh, okay.
Yeah. So good. If we instead allowed stuff to leak at the boundary, I mean, we could do that. No, there's no rule that we can't do that. But then we won't get a system that makes sense by itself. Then we need to say where the stuff is going, and then we need to introduce more stuff. The duality didn't say AdS plus more stuff equals CFT. So. We could also write down a duality like that, but let's start simple. Yes? Yeah. 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 With a finite cutoff, that's true. But again, so with a finite cutoff, then we don't get to write this equation. Then we write CFT with a UV cutoff, right? So.
I mean, my question is that from this cutoff, it seems each boundary condition is unit, but I can also see why when we take this cutoff, we just choose one boundary.
Yeah. Let me make a slight comment about that at the end. But roughly speaking, you really have to quantize to really see that. But there's a current that's associated with the wave equation, which is called the Klein-Gordon current. And you want to say that the flux of the Klein-Gordon at infinity is 0. Now, from the classical point of view, that's just a choice. I mean, I don't have to do it. Classically, unitarity doesn't mean anything, right? But if I want that current to be conserved, which corresponds to the number of particles in AdS. So if I want that to be conserved with time, then there better not be Klein-Gordon flux at infinity. And so that's the choice that I'm making here. And once we quantize, we'll see that has to do with unitarity, because that's what keeps the Hamiltonian or Hermitian operator within the Hilbert space. Yeah. What? Oh, no, you do have to worry about the boundary conditions at infinity. I mean, I should clarify, though. Good. An important difference here is that if you're sitting in the center of the bulk, in Minkowski space, who cares what the boundary conditions are? Because it takes infinite time for anything from the boundary conditions to affect you. But here, if you wait for this time of order pi, then the boundary conditions hit you right in the face. So I wouldn't say it's not an issue there. It's just it's really an issue here. Like, we can't discuss the theory, even just from the point of view of someone sitting in the center without talking about the boundary conditions. I mean, in Minkowski space, we should be careful about it too, but people usually aren't because the choice doesn't affect you if you're sitting in the center and living for finite time. Yeah. Okay. Okay. So those are the classical solutions. Let's now just quickly quantize. So to quantize, we promote phi to a Heisenberg picture operator, where we have a sum over this NLM, this FNLM. So now I've abused notation and I've replaced F omega by Fn, but you know what I mean. Function of R, T, and omega. And now there will be coefficients which are operator coefficients, ANLM. And then there will also be a complex conjugate, star ANLM dagger. So here this is a real scalar field. So then now to do quantum mechanics, what we should do is we should take these A's and A daggers to be creation annihilation operators for particles. So in particular, we want to have that A n L M, A n prime, L prime, M prime dagger is delta n n prime, delta L L prime, delta M M prime. And so actually by normalizing the creation annihilation operators this way, I've also implicitly chosen a normalization for these F's. So let me just be explicit about that. The normalization that I've chosen is that in this Klein-Gordon norm I mentioned, where the inner product of two solutions of the Klein-Gordon equation, which is here just this del squared equals m squared equation, is defined as the integral over some time slice sigma okay, so let me write this carefully. G star d mu f minus d mu g star f. So sigma here is any time slice. N mu is the normal vector to that time slice. I'll just say, in good conventions, it's unfortunately true that the normal vector with the index upstairs is past pointing. Just live with that. If you don't like that, you can switch the convention and put a minus sign here. And then this is the induced metric on the time slice. Okay. And you can, again, in your dorm, if you haven't before, you can convince yourself that this definition is independent of which slice that you choose. You have to use the equation. You have to use that these guys obey the equation of motion when you do that. Okay. So then the rule is if we take f to be Kronecker delta normalized in this norm, then that implies, if you like, the canonical commutation relations of phi and phi dot imply that A and A dagger obey the usual operator algebra. Yes?
So assume that the normalization of the y element that
Oh, yeah. So I certainly assume the standard normalizations for these guys. So yeah, I guess the integral of y star times y is a Kronecker delta. Yeah. Well, okay, I think, isn't that the standard normalization? Okay. Okay, good. Thank you. All right, good. So for the scalar field in AdS, that's kind of all there is, right? So for each n and L and M, right? So we can define a ground state. Maybe let me call it 0, which is annihilated by all of the NLMs. Okay, that's the vacuum. No particles in AdS. And then particle excitations are created by acting on this with the A daggers. And there's a discrete set of particle excitations, which, again, you should think of as being consistent with the fact that you're living in a box. Yes?
Especially if you're ignoring the back reaction, it's fair to say that you should only consider excitation up to AdS scale?
Well, I think you mean Planck scale. Yeah. So you're absolutely right that I've ignored back reaction here. That was just because I wanted to start with something simple. We eventually do, of course, need to include gravity into the story, but the back reaction is suppressed by G Newton. which, as Joanna explained, there's a large parameter that separates the Planck scale and the AdS scale. I'll say a bit more about that later in the lecture. But, I mean, eventually, yes, we absolutely need to do that. I'm just warming up here. OK, yeah, other questions? That's all I wanted to say about the bulk, so I'm going to switch to CFT now. All right. Oh, we've got these tiny little erasers. Oh, OK. Yeah, work hard. Good. So on to CFT. So Joanna said quite a bit about this already, so I'll try to keep it to a minimum. So conformal field theory is a relativistic quantum field theory, which, in addition to invariance under the Poincare symmetry generated by J mu nu and P mu, also has additional symmetries, dilatations and special conformal transformations, which are generated by this K mu and D that she was talking about before. So the conformal group is generated by J mu nu and P mu, which are usual Poincare generators. Then there's a dilatation operator D, and then there's special conformal transformations K mu. And as Joanna explained, these are defined as the set of coordinate transformations which preserve the Minkowski metric eta mu nu up to an overall multiple by a scalar function. So this group is isomorphic to SOD comma 2, which is nice because we were just discussing that group a few minutes ago. And so then all of the operators in the theory transform under these symmetries. In particular, there are two kinds of operators that were especially there's a kind of operator that we especially like, which are these primary operators. Joanna called them quasi-primary, but that term only makes sense in d equals 2, and so since I usually like to live above d equals 2, I'll just call them primary. In d equals 2, I would call them Virasoro primary versus global primary. But the term primary is so nice. Shouldn't we be allowed to use it for something in higher dimensions?
Yeah, but primary refers to the
Yeah, there's the group. Well, okay, let me write the definition then, and then we can agree it's. It's just terminology. So okay, then I'll be careful to state the definition. So primary operators have two special properties in how they transform under conformal group. So first of all, if we conjugate a primary operator O of x by a dilatation, then it rescales like e to the alpha delta O of e to the alpha x, where delta is the conformal or scaling dimension of O. Okay. And actually, this is true not just for primary. So any operator that transforms like this, we say it's an operator of definite dimension, and its dimension is determined by the delta that appears here in this equation. Okay. But then primaries are special. So primaries obey an additional thing, which is that if I act with a special conformal transformation, I don't know, lambda mu, and now I put the operator at 0. So here again, we're working in Minkowski space. This is the origin. So the split into J mu and P mu and D and K and so on, it makes reference to a choice of origin, right? The J mu's, for example, generate Lorentz boosts around a specific origin. And so that's the origin that's going here. K mu, lambda mu. And then for a primary, the rule is that this has to be invariant. So we just have to get back O of 0. Okay. And so in my convention, a primary operator is anyone that obeys these two things. Yeah, so you call it a quasi-primary. If you like more syllables, that's fine. I won't stop you. All right, now we're going to have to do lots of erasing. Okay, so in addition to primary operators, as Joanna explained, there are also descendants. So descendants are operators that we get by acting on primaries with derivatives. So for example, if O is a scalar primary, then d mu d nu O is a spin 2 descendant. And in fact, the nice thing about descendants is that if O is a primary and then we act on it, with d mu 1, d mu n, something like that, then the scaling dimension of this is just the dimension of O plus n. So the scaling dimensions of these guys are just go up by integers compared to what the primary had, but they will no longer obey this second condition, so they will not be primaries. In fact, the only way for a descendant to be primary, I think, maybe she can correct me, is if it's 0. I think as long as you take number of derivatives, no matter how you contract them, if it's not 0, then it's not a primary. I think that's true. Okay, so now the most fundamental fact about CFTs is that the set of primary operators and their descendants gives you a complete basis for all the local operators in the theory. So when we talk about all of the local operators, it's enough to just talk about the primaries and their descendants. And not only is that true, even more is true. So the set of primary operators and their descendants are in one-to-one correspondence with a complete basis for the Hilbert space of the conformal field theory quantized on a spatial sphere. So let me try to be a little more clear about that. So say here we've got there's a map called the state operator correspondence. So the map, given an operator, it makes for you a state of the theory on the sphere, and given a state of the theory on the sphere, it makes for you a local operator. So let's say we were given the operator O. So the rule is you take O and you put it in the center in the origin, and then you draw a sphere around it. So in higher dimensions, this is a ball centered on the origin. This guy is sitting in the center of the ball. And then we just do the path integral of the theory over the interior of this ball with some boundary condition on phi on the fields at the edge. And so this defines a functional of the fields phi, where phi here, if you like, is a map from SD minus 1 to whatever the target space of the theory is. Okay, so this is a state of the quantum field theory, but now quantized on a sphere. These functions like this are precisely those things. Yeah.
Are there normally a square number of operators per state? Is it because these are only the local ones, but there's a one
We're talking about local operators. Yeah. Well, so far I define the map one way. So to show you it's a bijection, I have to work a little bit harder. Everyone knows what a bijection is, right? One-to-one and onto. Okay, so this way, given a local operator, I put it here, I do the path integral, I get a state. Okay. Now, to go the other way, okay, the rule is now we just start. So now we just start with a psi of phi. Okay, that defines some functional on functions on the sphere. So then the rule is, well, whatever this state is, I can just do a dilatation, and I can move it into the center to a smaller and smaller circle here. And then I can, by doing that, I can produce an operator where, were I to stick it into the path integral and then dilate it back, I would have gotten the state that I started with. And so that's the inverse map. Note that I had to use the dilatations to do it. So that's a property of conformal field theories, not of quantum field theories in general. Yeah. What it means to do the path integral? Yeah, well, that's a sort of general embarrassing question about conformal field theories. So, if you talk to the cognoscenti, right, like Xi and his friends, they'll tell you that a conformal field theory is defined by a set of local operators and OPE coefficients, and words like Lagrangian and path integral are never mentioned. But if you ask them, what are the rules that these things need to obey? Where do you get the rules from? Then they write down a path integral and say, oh, it comes from the path integral. So I don't know what to tell you. This is just this kind of funny state of conformal field theory where, I would say I don't think there's a good way of coming up with the rules other than by doing formal path integral manipulations. But then once you've done them, then you just say, okay, these are the rules, forget about the path integral. I don't know. She may comment on that in his talks more. I don't know. But yeah, that's right. But why is that the definition, right? I mean, instead of something else, right? I mean, yeah, I don't know. Yeah, I'm sorry. I mean, I don't know. In 100 years, when we know the correct definition of quantum field theory, I'll be able to give a better answer to that question. Okay. So good. Now, so the state operator correspondence, it has one very nice property. So far what I said is true for any local operator. But we have these really nice local operators, these primaries and these descendants, right? So what kind of states do those get sent to, right? So then the idea is that primaries and descendants are in one-to-one correspondence with eigenstates of H on S d minus 1, with eigenstates of the Hamiltonian of the theory quantized on the sphere. And moreover, the energy of the state that we get from an operator O is just equal to the scaling dimension of the operator O, possibly plus an overall shift, which is called a Casimir energy, and which is the same for all the operators. Sometimes this Casimir energy can be removed by a local counter term, but sometimes it can't, so we have to keep track of it.
So the first subscript is a curly O, but the second subscript
is a 0. Yes, I'm sorry. Yes, so this is the ground state energy. So this is, so if we, good. So for example, a good example is, say we take the operator to be the identity. It's my favorite local operator. Okay. So if we do the identity here, then we're just doing the path integral on the disk, and that defines the vacuum on the sphere, the ground state. So then apparently the ground state is dual to the identity. So then for the identity delta 0, so then we just get the ground state energy. Okay. So to understand this, what we have to understand is that the Hamiltonian on SD minus 1 is really just the dilatation operator on the plane. Yes?
It's not immediately obvious. Why is it that just doing the path integral? Well, maybe if you.
I think if you just wait 2 seconds, I think you'll be happy. Yeah. Okay. So we have to understand that the Hamiltonian on the sphere is the same thing as the dilatation operator on the plane. Okay. So to understand that, what we do is we start in the plane, and we work in polar coordinates near the center. dr squared plus r squared d omega d minus 1 squared. So then now if we make a coordinate transformation, r equals e to the tau, then this just becomes e to the 2 tau times d tau squared plus d omega d minus 1 squared, right? And so now you see here, this is basically the Euclidean cylinder. So then finally, if I define tau equals IT, then this just becomes studying the quantum field theory on a Lorentzian cylinder. So then you see that, so what did dilatations do anyways, right? So we saw dilatations multiply all the coordinates by e to the alpha. But since r is e to the tau, then dilatations just shift tau by alpha, right? But so then when we continue to Lorentzian signature, shifting tau by a constant is just time evolution. So the operator that generates that has to be the same operator that generated these rescalings. So it has to be the dilatation operator, and then this is true. All right. So that's sort of CFT 101. I think that's basically all I wanted to say about it. So hopefully this stuff is familiar to most of you, but anyways, I think it's good to get it all out, because I'm going to be using these terms in passing later, so I don't want anyone to be confused. All right, so any more questions about CFT? So I'm supposed to stop at noon, right?
Correct.
Okay, great. If that were noon plus or minus epsilon, what would the epsilon be? Like 5 minutes is a reasonable epsilon? Sure. Okay. It wouldn't be more than that. I know people would be hungry, so I don't want to. Yeah, that's right. So. Yeah, but we're having so much fun.
They're going to be having fun 3 or 4 times a day, 5 times a week.
I know, but I'm in the first week, so I don't have to suffer. You know, when I came to TOSI, I computed. I went to 76 talks. I promise. Well, I was physically present for 76 talks. I'm not sure if I was mentally present for. Well, anyway. Okay. Good. So now, all right. So preliminaries out of the way. Now let's state the correspondence more properly. Sorry, what? Yeah, so there is, yeah, good. So this is not strictly a conformal transformation. So when I do this, there will be a Weyl anomaly. That's true. Yeah, that's related to this shift here, actually. Well, I think I use the fact that I know the Weyl anomaly is a scalar functional of the metric. I was very implicit in how I used it, so it probably went by most of you. But yeah, you can certainly be careful about the Weyl anomaly, and what I said is true, and I think that the anomaly, roughly speaking, generates this. No, I think it's not, because so if you think about it, the trace of the stress tensor what appears on the right-hand side has to have a certain dimension, and it's very limited what things can appear there. So usually you don't have other things that can appear there besides a C-number functional of the metric and the curvature. I don't know of any example where the Weyl anomaly has a non-trivial operator on the right-hand side. I kind of suspect you would need to have some free theory, and then because it was free, maybe the anomaly wouldn't be there. But I'm not sure. Yeah. Okay. Good. So let's now state the correspondence. So here's the claim. So any CFT on SD minus 1 times R, where this one we should think of as Lorentzian time, defines a theory of quantum gravity in space-time, which is asymptotically AdS d plus 1 times m, where m is compact. Okay. And moreover, we require that as we approach the asymptotic boundary in the AdS directions, this m stays finite size in AdS units. Okay. So I could say finite at boundary. Okay. And so this m is kind of annoying, so for the most part I'm just going to ignore it and not have the m, but it's kind of unpleasant that when we actually have examples of AdS CFT like the ones Joanna was talking about, where we know how to compute things, there seems to always be this m, which is very aggravating. So I have to include it in the definition. Okay. So that's it. That's the statement. Any CFT on SD minus 1, you get a theory of quantum gravity in AdS. Now, there are a few obvious questions that have probably occurred to most of you. Well, probably occurred to you long ago, but if they didn't occur to you long ago, they probably occurred to you now. So one is, okay, what is the map? Right, so given an observable on one side, how do I know what's the observable on the other side? And secondly, so which CFTs give a bulk which is semi-classical? Right. And the second question is quite important, right? Because, I mean, a free massless scalar is a CFT, okay? But it's not, any interesting kind of quantum gravity in one higher dimension, right? I mean, we could imagine that it's some very complicated quantum gravity, which looks nothing like the gravity that we see all around us. And I guess the way I phrase the definition, that's what I'm saying. But interesting examples of AdS CFT will be ones where the bulk looks something like the gravity that we're actually interested in the real world.
So why do you want the gravity to be semi-classical?
Well, I guess that's kind of an emotional question. Why do we want it? I mean, I want it because, there's gravity in the world. I drop this, it falls. It has to be consistent with quantum mechanics. I want to know how that works. So if the thing you got didn't have a limit where, you could do the solar system and, LIGO and this kind of thing, to me it's just not interesting. I mean, otherwise anything is gravity, right? I mean. No, CFT. No. So if you have some sort of RG flow or something, it actually breaks the asymptotic symmetry. So here when I say, I mean, yeah, here I haven't defined AdS asymptotically AdS very carefully. That was that paper I said you should all read. But in that paper, when they define asymptotically AdS, they define it to preserve the conformal group acting within the Hilbert space and preserving the ground state. So something within RG flow is not included.
But CFT should be conformal. Okay, so conformal is
Well, no, RG, so yeah, okay, this is a constant confusion. So let me state very categorically. So there is an alternative way of thinking about AdS CFT where the interesting thing to do is to turn on deformations of the CFT and probe the physics that way. I will never do that in these talks ever. Okay, I'm interested in the Hilbert space of the CFT on the sphere. I don't want to turn on any deformations. It's a very interesting theory all by itself. It has many states. It has black holes. I never want to turn on boundary conditions. That's changing the theory. That's not an operation within the Hilbert space of the theory on the sphere. It's a different theory. And it's interesting to study. I'm not saying it's not interesting to study, but we're going to have our hands full just understanding the ordinary Hilbert space with no sources turned on at the boundary. Okay. Let me see. I mean, maybe to elaborate on that further, right? I made that choice when I made the plus sign choice here with the boundary conditions. That says no sources, right? So that was what I called non-unitarity. Non-unitarity is when somebody comes in from outside the system and kicks it at some random time that you can't predict within the system, right? And then later something, maybe something comes out or is absorbed later or something like that. Well, the RG flow is trivial for an exactly conformal field theory. Right. That's the whole point.
Yeah, so exactly.
Yeah, but that doesn't mean it's not interesting. I mean, there are thousands of papers written about conformal field theories, even though they don't have any RG flow. Yeah. That's right, but there are certainly excited states. I mean, there are states of non-zero energy.
Right. So I want to talk no RG flow, it's just AdS lab.
No, because the ground state of the CFT corresponds to empty AdS. But there are many other states, right? And those states, for example, some of them we get by taking these A daggers and acting on the vacuum, and then now there are particles flying around in the bulk. And those states are not conformally invariant, right? There's a particle here and not there.
So this is, okay, so this is equivalent to the other picture where you
No, it's not. It is not equivalent to that. No. The Hilbert space is the Hilbert space of the CFT. No source is ever turned on. there are some computations on one side which can be related to computations on the other side. But to me, a theory is a Hilbert space and a Hamiltonian. And that's what we're doing. And in that Hilbert space and Hamiltonian, we can compute everything. We never change the Hamiltonian or the boundary conditions.
So there are two ways you can deform pure AdS. There's sort of sources at the boundary, or maybe turning on Vebs at the boundary. The first kind changes the theory, and that's what Dan is not doing.
Yeah.
The second kind just takes you to a different state within the same theory.
Right.
Both of them move from AdS to some asymptotic AdS, but we're only considering one kind here.
Right. You just put some stuff in the bulk, right? You're allowed to put some stuff in the bulk. You don't have to change the boundary conditions. Right? Oh yeah, that's why I said asymptotically, right? So, yeah, that's true. But I just right, fair enough. Yeah, I at least wanted to include this so that people don't tell me there's no examples. But right, we can always elaborate, further. Yeah. I mean, a lot of the rules I'm going to make here, are designed to make things well defined and interesting. But there's always things you can sort of quarrel with. Okay, good. So let me first try and say a little bit about what the map is before I get into this question of which CFTs are the good ones. So the basic idea, so the answer to 1 is called the dictionary of AdS CFT. It tells you, given a thing on one side, what do you have on the other? And I should say straight up from the beginning that we don't know everything in the dictionary. We know some things in the dictionary. The dictionary is a thing which so far has been expanding with time as we understand the correspondence better. And during these lectures, we'll see that it's gradually expanding. But we'll start with the most basic elements of the dictionary and then work out from there. So the most basic element is that there's an isomorphism of the Hilbert state basis. So a state in H-AdS is in one-to-one correspondence with a state in H-CFT. So one we already discussed is the ground state. The ground state of the CFT corresponds to the ground state in AdS, just pure AdS, nothing there. There are also excited states, for example, we get with acting with the A daggers, and those also have to correspond to states in the CFT. And we're going to discuss in detail how that works in the next lecture. Yeah. Well, yeah, it depends what you mean. So gravitons are low-lying, individual gravitons. If you want to make coherent states of gravitons, then those are higher energy. Yeah, we're going to discuss this more. Yeah. But not only are the states in one-to-one correspondence, but the symmetries are in one-to-one correspondence. So these generators are in one-to-one correspondence. So for example, the spectrum of the Hamiltonian is the same on both sides. For every eigenstate of the Hamiltonian in the CFT, and remember we're on the sphere, so an eigenstate of the Hamiltonian just corresponds to a primary or one of its descendants. Then in the bulk, there will also be some state with that same energy. And more generally, the whole representations of the conformal group, the whole decomposition of this Hilbert space into representations of SOD, 2 is the same as the decomposition here. So every irrep appears the same number of times on both sides, if you want to be mathematical about it. Now, unfortunately, without answering question 2, I think this is about all I can say. So, this is related, so it's kind of a trivial correspondence. Okay, the symmetries are true, great, and that's associated with the fact that if the bulk is very quantum, we kind of don't really know what else to study, right? We don't have any other observables where we can ask what is the CFT version of those observables. So to do better, we're now going to have to start dealing with question number 2. And I guess we'll start dealing with question number 2 today, and then we'll say more about it tomorrow. 3, yeah. Plus 5. I didn't say plus 20. I said we started late, right? So Okay. Good. So let me just close then by saying trying to give a sharper definition of what it means for a CFT to be semi-classical. Okay. So here's a definition. So a CFT-D is, or how shall I say? I should say has a semi-classical dual if. So then there will be two things that we want. So one is that there exists a local bulk effective action, S effective, which has some finite number of bulk fields, and it also has a cutoff. And there exists primaries, O sub I, such that, well, let me try to write this out carefully. If in the bulk, and I should say this, so there are finitely many phi I, and one is the metric. So the bulk theory has one metric field. Well, I could keep saying, I could say, okay, the action is local, it's diffeomorphism invariant function of the fields. Okay, probably you're willing to assume these things. Okay, so then if we do the bulk path integral over the phi's, e to the I s effective, of a certain set of operators which I'll call OI, of T1 omega 1, O I n of Tn omega n, then we get, just in the CFT, the expectation value of these primary operators, O omega 1, O I n, Tn omega. Okay, we're now I need to tell you the map between the O's on the two different sides. So on the bulk side, when I write a OI of T and omega, what I mean is I take the limit as r goes to infinity of r to the delta I, phi I of r, t, and omega. So this is called the extrapolate dictionary of AdS CFT. It says you take a bulk field, like this phi I, you move it to the asymptotic boundary, rescaling it by the conformal dimension of some operator in the CFT, and then whatever point you pull it to, which is labeled by this time and this angle on the sphere, you just get that primary operator at t and omega. Okay? And this is an operator equation, right? I'm saying that it holds in correlation functions with arbitrary other operators here. And now I have to put caveats. So this is true. So I should really put a approximation there. And then I should say this is true to all orders in 1 over this cutoff times the AdS radius for n, which is order this ratio to the 0. Okay? And this gets at someone was asking about back reaction before. So this is saying you take a finite number of fields in the bulk, which is order 1 compared to the cutoff size in AdS units, and then you extrapolate them to the boundary using this map, and then that's the same as the correlation function, all in Lorentzian signature, of these primary operators in the conformal field theory. Okay? Might be a lot to digest. So let's stop and ask. Questions? Well, that's a definition. I called it semi-classical. Yeah, so that's sitting good. So that's sitting inside of this S effective. So, oh, good. Sorry, there's one other, good. There's a line I forgot. Let me put it here. And I want that lambda has to be less than 1 over L Planck, which, let's see if I can get this right. I think it's G to the minus 1 over D minus 1, where G appears in S effective. Okay, so there's an Einstein-Hilbert term in S effective. It has a coefficient G that defines a Planck scale, and our cutoff has to be at most that scale, and it could be lower. For example, it could be the string scale. All right. Yeah. Why is it a reasonable definition? Well, you know, all I can say is that this is what I want. I don't know, right? I mean, this is so if we were doing quantum gravity in flat space, I think this is what would satisfy me, right? Like, this is what would let me show that by using whatever the quantum gravity theory is, I can reproduce bulk effective field theory to all orders in G Newton, right? So this is to all orders in G Newton once we, or possibly a lower scale, you know, if there's strings or something. So I don't know what to tell you. I mean, yeah, I guess it's maybe psychological, but this is what I want. You know, I want to be able to reproduce Feynman diagrams in AdS, including the metric, you know, starting from the CFT, in some limit where there's a reasonable chance that could happen. Now, okay, let me just close 30 seconds to make so probably on some level I think this definition is sufficient, but there's one extra thing in the definition that I want to add. I think it actually follows from this, but I don't know how to prove it, so I'm going to add it. So I said there were two things that I wanted. So this was one, and then the other one is that. So I want to say that the thermal entropy in the CFT for T larger than 1. Where here 1 is the size of the sphere in the CFT. The CFT is living on a spatial sphere. Matches to all orders in 1 over lambda L, the black hole entropy computed from S effective. Okay. And so for me, this also has to happen for me to be satisfied. So in particular, if S effective, say that we're just working to leading order and it has an Einstein-Hilbert term, you know, R over 16 pi G, then what this says is that if you compute the thermal entropy in the CFT at sufficiently high temperature, you should get A over 4G, the area of the horizon of the Schwarzschild solution in the bulk. Okay. So roughly speaking, the first condition we need to get particle physics right in the bulk, and the second condition we need to get black hole thermodynamics right in the bulk. Now, I actually don't know of any examples which satisfy that but don't satisfy that, and I would be shocked if there were any examples. But I don't know a proof, so I thought I would add it. Yeah?
In the first case, are you referring to CFT Euclidean space? Or
No, Lorentzian.
Oh. But if you allow let's say,
Yeah, sure. Yeah, so if right, fair, no, yeah, that's fair enough. That's fair enough. Yeah, that's fine. Fine, I agree with that. Yeah. So, and indeed, I probably do want it to be true on any manifold. So, yeah, sure. Yeah, I guess what I meant was that I don't know a Lorentzian way of kind of counting the microstates. Yeah. Yeah. I'm not sure how to say. I mean, I don't know. I don't think well, since everything was Lorentzian, I didn't explicitly use the state operator correspondence, but the state operator correspondence is true, so I should be allowed to use it if I want to, right? Oh, yeah, but sure, but I don't need to, yeah. So this was just, all I used this for was to motivate this relationship between the operators and the states on the sphere. But yeah, indeed, we think the correspondence should be true on sort of any boundary Euclidean manifold. Yeah, but well, I don't know what to say. I mean, usually it's not a thing we prove. So if we assume it, I mean, she is right that if we assume it, then this implies that. So I should have said it that way probably. But I mean, yeah, we can also. It might even go the other way. This in Lorentzian signature and this might imply it on all the other manifolds. I don't know. Yeah.
So let me just say, it's getting kind of like...
Yeah, I'm done. So I'm done. So.
Okay, so
yeah.
we'll also, in the afternoon, she and will be talking, that we also have a discussion section at the last of the 4 slots today. So if you didn't get a chance to do questions now, there'll be time at lunch and also then to talk to the speakers. So let's thank Dan.